Hey everyone, in this video we will be talking about how to use the definite integral to calculate arc length. So let's consider this example here. So we've got the square root of 4 minus x squared, and so this is just a semicircle, right? So we're actually going to be able to compute the arc length exactly here because the arc length is just 1/2 of the circumference. And we know how to do the circumference, right? So this is 2 pi r. My r here is 2. And so this ends up being exactly 2 pi, right? This length here that we're tracking. But imagine that you were faced with a curve that was not so familiar. So this one I'm doing just because I want to compare our approximation to what we actually know it to be. But suppose you have a parabola like x squared, for instance. We don't know exactly what that curve is going to get us between any 2 points. If you have the exponential function e to the x, that could be hard. So what we're going to do is something we've done a lot in calculus and do kind of a limiting process here. So we're going to start with things that we do know. So we do know how to take the length of a straight line, right? So let's consider just a few points here. I'll just do the points with integer x values. And essentially, instead of doing the arc, we're going to do straight lines between any of these 2 points, right? Between the 2 consecutive ones, sorry. And so basically, we can add these up, call this like C1, C2, C3, C4. We add up these guys, so the length of these should be approximately 2 pi. Okay, and we see here this should be an underestimate, right? Because these guys are a little bit shorter. But you can imagine that if you take more and more points closer and closer together, and then add up these lengths of the straight lines between them, that you're going to get a very, very good approximation of the actual arc length. And that's the kind of limiting process that makes you think, okay, we're approximating something by taking these things close to it. I mean, it sounds a little bit like what we did with the derivative there for like the tangent line and the secant lines approaching them. And then we're adding these things up. And if you're adding more and more and more, like an infinite sum should make you think of Riemann sums. And so actually here, both the integral and the derivative show up. Okay, so now we should be concerned about how to actually find the distance between these. And this is just the distance formula, right? So I have numbered my point or labeled my points. And so all this is saying is how do we get from one to the next and how far is that going to be? And from the distance formula, we know that it's going to be exactly this, right? And so we just want to add these up and see what we end up getting. So C1 here, right, we are going from -2 to -1 in the x. So that's going to be a 1 squared over here, right? There's a distance in 1. And then we have gone from 0 in our y value to the square root of 4 minus 1. So square root of 3 squared. So this is actually just the square root of 4 or 2. And by the way, you should notice that these are symmetric. And so C4 is 2 as well. And then for C2, what we are doing, again, we're only going 1 to the right, from -1 to 0. So we have 0 minus -1. So this guy's 1. And then here, x2 is at height 2. And that's coming from height of root 3. And so this squared, and you'll just have to trust me that this is roughly like 1.035. And so similarly, right, C3 is equal to this, and so by symmetry. So it also is about 1.035. And so what do we get when we add them all up? So we end up getting 2 plus 2 is 4 plus 2.07. We get about 6.07. So I'll say 6.07-ish. And remember what we should have gotten was 2 pi, which is, again, approximately 6.28. And so we're already pretty close. And so we can see that, okay, seems like a good process, but like how does this actually lead to calculus? Okay, so thinking back to our last example, right, I said like my length of the ith segment is this from the distance formula, and then our arc length, right, should be, okay, our approximation would be this guy, just sum up the lengths of those straight lines, and then if we want to actually get the arc length, right, we want to be extremely accurate, we're going to take the number of these off to infinity, right? Get our points super close together, get a whole bunch of really short, tiny line segments that perfectly approximate our curve. So the key is to actually rewrite CI to see how this ends up being an integral involving the derivative. So we can rewrite it like this. So what have I done? All I've done is multiplied by xi times xi minus 1 over xi minus xi minus 1, where I am distributing the division throughout the inside. Okay, so that's how I'm rewriting this inside, and then I leave the multiplication outside. So why does this help us? Well, what is this? This is rise over run. This is our slope, right? This is roughly f prime of xi. And then this guy is your change in x. This is your delta x. So what are we really summing up? We have the square root of the derivative squared plus 1 times the change in x. But this is a Riemann sum, right? We have this delta x on the outside, and we've got our test point on the inside. And so when we take the limit, as n goes to infinity, this is exactly your integral on whatever you're trying to get the arc length on, that interval from a to b, of the square root of f prime of x squared plus 1 dx. And so this is our arc length formula in general, which seems nice, except for this in general is very hard to compute. For most examples, it's actually like not going to really be possible. So including the last one, it would have been really tough, but the one I will give you here as your exercise is one that is doable. So let's see. So first I want you to use these 5 points to approximate the arc length of the parabola x squared from 0 to 4. And then I want you to set up the integral for the exact arc length using the arc length formula, and then state what method you think you should use to solve that integral. I'm not requiring you to actually go ahead and do it, but you should see how to start. All right, thank you for watching.